Hello folks, and welcome to the channel, or welcome back. And in this episode we're going to dig deep into the CAN synchronization. And you probably know that we've made a couple of videos on the CAN bus so far. We did one on the physical aspects, the cabling, we did one on the electrical aspects, and then we did one on the protocol itself, and then finally we did a decode on an extra video of one of the data frames on the CAN bus. And within part 3, I explained a bit about synchronization, hard synchronization and kind of soft synchronization. And I mentioned in that video that you could actually ask for a more detailed video on bit timing on the CAN bus if there was an interest in it, because it's becoming really technical. And that's what this video is now about, because one of the subscribers did request a deep dive into the bus synchronization. The CAN bus is a two-wire system, and some people will say that the CAN bus is an asynchronous system, and other people will say it's a synchronous system. Let's have a quick look on synchronous versus asynchronous communications. The first example is a very old example where we had a data circuit equipment, for instance a modem, and a data terminal equipment that could have been the PC. And I know for most of you guys this is something from the far past, but that was a typical synchronous timing arrangement whereby the data circuit equipment, the modem, would provide a transmit clock to the data terminal, and it would also provide a receive clock to the data terminal. So the data terminal is slaved off the timing of the data circuit equipment. And in this way, we can talk about synchronization or timing. Another example is whereby we do not have all these separate wires, but we are kind of embedding the timing into the data signals. And this is what we refer to return to zero synchronous timing. So the gray box is what we call a bit time, right? So this is a bit 1. This gray box right here is bit 0. And this gray box here is a bit 0, and then we have another bit which is a bit 1. Now there could be any sequence here, I'm just giving an example. But what you can see, halfway the bit time, the signal drops back to the 0 level. So this way we can always extract a clock signal out of that data stream, no matter what the data pattern is. Even if you have consecutive ones, you still will have edges that are going to fall back down to the 0 level. And that's one way of retrieving timing. It avoids having separate wires for transmit clock and receive clock. As you have seen before, in the DC-DT synchronous timing arrangement, we do require separate wires for transmit and receive clock. Now on the CAN bus, we don't have this. We only have CAN high and CAN low. But on the CAN bus, we don't have return to 0 either. We have non-return to 0, because our 1 bits, they stay 1 the whole time of the bit time, and a 0, they stay 0 the whole time of the bit time also. So we need to find another way to synchronize the CAN bus. Now let me give you one more example of an asynchronous solution. You might remember teletypes, and teletypes used to work fully asynchronous. They consisted of a Bordeaux code, which 5 elements, element 1, 2, 3, 4, 5, and that would represent the letter. But the start of the letter would always be with a start signal, and the end of it would always be with a stop signal. And the stop signal would typically be 1.5 the times of an element, or 2 times. Well, the reality is that the CAN bus is actually both. It is, from a pure bus perspective, an asynchronous system, because it has no signals on the bus that are referring to a clock signal. There is no transmit clock, there is no receive clock on the bus. And the data is actually not returning to 0. So we talk about a non-return to 0 data pattern. So the data frames that are being sent, when a bit is 1, the bit stays a 1 during the bit time, and when it's 0, it stays at 0 during the bit time. It does not return back to 0 like you would have with other mechanisms. So if you have a return to 0 solution, then you actually are embedding a clock signal into the data stream. But we have none of that. But still, the bits that are being transmitted by a CAN device are transmitted out on the transmit clock, and the receiving CAN devices have to be able to read that bit in at the right time, probably around 2/3 of the bit time. And therefore, reading in the bits is going to require a receive clock. And that receive clock is locally generated in every CAN controller. So in other words, all CAN controllers have what we call an oscillator and a phase-locked loop system. And it's a combination of the oscillator and the PLL, which is phase-locked loop, that will make sure that we have the proper readout of every bit on the bus. So let's look at a slide what I mean with this. So let's have a look on the CAN bus ISO 11898-2 on how synchronization takes place. Now before doing so, let's have a look why we need synchronization. Now imagine that we have a CAN controller and it's going to transmit some data out, and it has its own oscillator, and we have other CAN devices on the bus that will receive that data, and they are running on their own oscillators. And the oscillators on all the CAN devices are not in sync, they are not synchronized. Let's say we have like 180 degrees phase offset on the red one. So when data needs to be transmitted, the bits have been put into the transmitter, and the transmitter will clock out the data bit onto the bus. And then the receiver will then clock in the data bit and then recover the bit and send it to the microcontroller. So let's have a look on how that would work if we have no synchronization between the oscillators. So we got our data bit coming in, and that's the beginning of the data bit, and this is the span of the data bit. And the bit will be clocked out onto the wire based on the leading edge of the transmit clock. And then the trailing edge of the clock ideally is in the middle of the data bit. And it just continues like this. The receiver will receive the signal, but as the receive clock right here is not in sync with the transmit clock, and we kind of said it's about 180 degrees offset, it's going to try to read in the bit. It's going to try to sample what is the value of the signal. Is it a 0? Is it a 1? But guess what? It is sitting right here on an edge of the bit. It's not in the center, it's not at 2/3, but it's right at an edge. So we don't know what we're going to read. Is it going to be a 0? Is it going to be a 1? It's hard to tell. This is an area where you should never read in or evaluate a bit. And that's because the receive clock has shifted from the transmit clock. Here you see the original transmit clock and how the receive clock is about 180 degrees out of sync. And that is why we need to have synchronization on the bus, so that all these oscillators on all the CAN devices are in sync with each other. And there's two ways of doing this. The point here is that all CAN bus controllers must have their oscillators synchronized with each other for proper transmission and reception of data over the CAN bus. We have two types of synchronization. We have hard synchronization and we have soft synchronization. Hard synchronization happens each time the CAN bus toggles from its idle state, which is all ones, to its active state, which is 0. That change in edge will actually trigger off a hard synchronization whereby all the oscillators will start syncing in with each other. So they all start their own timing at the right time. So they can actually read at 2/3 down the bit time the exact bit that is being transmitted, regardless if it's a 0 or a 1. That happens at every start of frame. So let's have a look on the hard synchronization. We have one CAN device which is going to transmit a CAN frame after the CAN bus was idle, and we have the other CAN devices that are going to receive that CAN frame. The oscillators on both sides are out of sync. So the clock of the transmitter, the blue one right here, is actually this clock that we have here on the transmitter. And the red clock that we see here, which is out of phase with the blue one, is the clock right here. And it's the receiver that will use the receive clock to clock in the data bits of the CAN frame. But right now, the CAN bus is still idle, and these clocks are running non-synchronized from each other. Now, we have the first transition of the edge, which is the start of frame bit. And the start of frame bit is the start point for the hard synchronization. The clock of the receiver is still out of phase, but because it has detected the start of frame, it's going to adjust its clock circuitry. And watch. It aligns it, and right now it is back in phase with the clock of the transmitter. And now we can clock in the bits in a proper way. But this is hard synchronization. That does not solve the issues of propagation delay over the link, because some wires are longer than other wires. It does not solve the issue of a slower or faster transmitter. And then we have the soft synchronization. You can imagine that the CAN bus has a certain length, so we're getting delays over the bus, and some devices are further away from the other device, so we have propagation delays. But we also have processing delays, and we have reading delays, and we need to compensate for that. And in fact, we might even have devices that are a bit slower. So this is where we're going to use the soft synchronization for, and that's going to be an adaptive adjustment within every bit time. And now let's look on how this is happening. The first thing we need to look at on soft synchronization is, when are we going to sample the data bit? And the sample point comes just after the phase segment 1. Now, don't worry about this too much. We'll talk about this in a minute. And this is a very specific implementation. This may be named differently on other hardware implementations, but in this case, this is what we're going to use. And that sample point typically is, as you can see, about 2/3 down the nominal bit time. And the nominal bit time, NBT, is the duration of a bit on the bus. And it's calculated 1 over the data rate. So if we're using a CAN bus running at 500 kilobits, then we just divide 1 by 500 kilobits, and that gives us an NBT of 2 microseconds. And we want to sample that at about 2/3 down. Now, in some cases, for very sensitive systems, we may sample that actually 3 times. And if we're going to sample it 3 times, then this is just going to happen about half a TQ before the actual sample point. Now, I used the term TQ, and you also see it here, TQ here. And TQ is nothing special. It's what we call time quanta, and we'll dig into that further on the next slide. We know that soft synchronization happens on CAN receivers at every bit edge, and an edge is at the end of a bit or the beginning of a bit. We already looked at the nominal bit time, the calculation, and this was just an example, 2 microseconds for 500 kilobits per second CAN bus. And our digital phase loop circuitry is going to use, in this case, 4 segments per bit time. So the 2 microseconds will be broken up into 4 segments for some very, very good reasons. And that will allow the DPLL to manipulate the clock so that we can stay properly in sync and clock in the data at the right time. Our nominal bit time is broken up into 4 segments: a sync segment, a propagation segment, a phase segment, and a phase 2 segment. Now you can imagine when the bits travel over the bus, some transmitters may be a bit faster than others, so we need to compensate for that difference in speed. We may also have some propagation delay on the network, so some controllers are further away from the sources, so the longer the wire, the more propagation delay we have, so things shift out, bits will arrive later, and we may even have phase shifts. So we need to be able to deal with faster and slower transmitters. We have to be able to deal with faster and slower processing. We need to be able to deal with longer and shorter propagation delays, and we need to be able to deal with phase shifts or phase issues on the receiving signal. And that is what the DPLL, or the digital phase loop circuitry, will do for us. And therefore, we have broken up the nominal bit time, which in this case is 2 microseconds into 4 segments, as you can see. So when a edge is detected, it has to fall within the sync segment. And when I say sync segment, that is X amount of time, a subset of time of the 2 microseconds. And we call this typically the time quanta, and this is typically 1 time quanta. And we'll look at that very shortly after this slide. If it falls outside the sync segment, then certain actions will happen with the clock. And I'll have some examples later in the slides on what will happen. We also have a segment that will deal with the propagation. So this will compensate for the physical delays between the nodes. And the propagation delay is typically defined as twice the sum of the signal's propagation time onto the bus. PS1 and PS2, those are there to deal with the phase errors on the edges on the bus, and PS1 can be lengthened, or PS2 will be shortened, all depending if the bit is arriving way too early or way too late. And of course, we can set the TQs between 1 and 8 or 2 and 8. Now, keep in mind that the TQs could depend from hardware to hardware. This is on a very specific hardware CAN controller. Other controllers may even be more smart, but this is one method we are trying to explain. Now we need to talk about the time quantum. Now we know that our CAN controllers, they all have an oscillator, and let's assume it runs at 20 megahertz, or it has a period of 50 nanoseconds. We know that our CAN bit time for the moment is 2 microseconds because we selected a 500 kilobits CAN bus. So we're going to divide the oscillator clock by what we call a baud rate prescaler. And in this case, the prescaler is set to 2. So in essence, we divide the clock speed by 2. Here we go. And this is 100 nanoseconds. So our sync segment that we discussed before is typically set to 1 TQ. So in this case, my sync segment will be 100 nanoseconds. So how do we come to this? Well, oscillator is 50 nanoseconds. Prescaler is 2. That sets my time, my TQ, to 100 nanoseconds. Now, how many TQs do I have in my total bit time? Well, how many times does 100 nanoseconds fits in 2 microseconds? And that's about 20 times. And therefore, we have 20 TQs that we can use across the CAN bit. And we can divide them up amongst the propagation segment, the PS1, and the PS2 segment. And how you divide them up, that's entirely up to you. Remember, the prop segment could be 1 to 8 TQs. PS1 can be 1 to 8, and PS2 could be 2 to 8. So we got 8, 8, and 7. So we are already way over the actual 20s. But you need to divide this up. Now, if you don't have enough TQs on your bus to adjust for the length and phase errors and all that, then you might have to change your prescaler. So that's a bit the principle, and that is a design aspect. When the edge is detected, it has to happen within the sync segment. We already talked about it. If it does not, if it comes too early or it comes too late, we will have to jump the clock back and forth. And therefore, we're going to use a synchronization jump width. So folks, as you have seen, within a bit time, we now have a sync segment, we have a propagation segment, and we have a PS1 and a PS2 segment intended to advance or retard the synchronization or the timing so that we can read the bits properly in. Now the question is, what can you do about the quanta? Now let's have a look on a edge of our incoming bit, which is falling nicely within the sync segment. And remember, in the previous example, our sync segment was about 100 nanoseconds. So we're expecting this edge to fall within this time period within the nominal bit time, which is 20 microseconds end to end. Now in this case, we don't have to do anything. There is no resynchronization necessary of our clock on the receiving side because the edge is exactly arriving at the time we expected it to arrive. So this is a pretty easy one. But what if the transmitter is faster? So basically, we are too slow on the receiving side. In this case, our incoming bit edge will be way out to the right. It will be detected. But the problem now is that we need to advance our clock. We need to speed up our clock basically to make sure that this edge is going to fall back in the next sync segment. And this is why we're going to shorten the phase segment 2. And the amount of shortening will be determined by when we detected this trailing edge within the phase 2 segment. And there we have the SJW, the jump width, and that's going to give us how many QTs we're going to advance the clock. And then the last one, we need to look at a signal that is coming in a bit too late. So we have our edge coming in, and it's not within the sync segment where it's supposed to be, but it's halfway down in the propagation segment. Well, in this case, what we're going to do is to delay the phase segment 1. And we're going to delay it with the amount that we have seen in the SJW of PS1. So we know when this was measured, what is the time, how many TQs have lapsed after the sync segment, and this is the amount of time we're going to delay the sampling point. So by extending the phase segment 1, in other words, we're going to delay the clock a bit. What I've shown you is one example on how a digital phase-lock loop system is working on CAN controllers. Now, of course, if you're going to develop your own CAN controller, you will have to check out what the datasheet says about your specific chip you're using for your CAN control. And then you have to make sure that you know all the parameters of the design constraint within your entire CAN bus system. Can you set all this up, and can you actually see this on the CAN bus when you're putting an analyzer up? And the reality is, well, if you're going to analyze the CAN bus with an analyzer, you're not going to see anything on this timing aspect because this is all embedded inside the CAN controllers. It is part of the oscillator circuitry, and it's part of the PLL, the phase locked loop circuitry of the CAN bus controller itself. On the other hand, if you're going to design a CAN bus system with all the different controllers, then you have all the controls to program up the controller on the CAN bus, and you will be able to set the jump register, you will be able to specify the baud rate calculation, you will be able to specify what the jump register value should be, and you will be able to specify how many quanta you will have within each of those segments we talked about. But that's really design work. So I hope that you enjoyed this video as much as I did, and I'll see you on my next video. Bye-bye.